Okay, so now we know that acceleration comes from force, but where does force come from? Well, let's go back to our x-axis. And let's put our body back here. I call this B1 because we're going to be looking at a variety of bodies. B1 is a body, an object of some kind. It has a mass, M1. It is sitting here at location X1. Now we're going to add something new to our universe, which we haven't seen so far, and that is the immovable object. So over here, and I'll just arbitrarily stick this at location 0, is our immovable object, and it's exactly what it sounds like. B is a movable object. This guy is not a movable object. And I'm going to connect my movable object to my immovable object with a perfect theoretical spring. It is like every spring you know, except this one happens to be perfect. Now, I'm also going to make another assumption, and I'm going to assume that there is no friction between my body and whatever it is it happens to be resting on. This is another of those mathematical simplifications that we like to do to keep things easy to talk about and figure out. Now, B1 is at rest. That means that it's not moving, obviously. And we know from knowing how springs work that if B1's not moving, then the spring is perfectly relaxed. It's not compressed, it's not extended, it's just sitting here perfectly limp and relaxed. So now I'm going to grab my body B1 and I'm going to pull it over here to some point, we'll just say X2. So I'm going to physically grab it and I'm going to pull it up to here. In the process of that, obviously I stretch the spring. And we know that when you stretch a spring, what does it do? Well, it exerts a force. When you pull a spring, it pulls back on you. So when I pull my spring over to here, when I pull B1 over to here, I now find that there is a force, I'll just call that F, exerted on B1. And if I was to let go of my body, B1, it's going to fly back this direction with some acceleration. I'm going to call that acceleration A1. So I have a body with a certain mass. I apply a force to it by stretching out the spring. I let it go, and it experiences a certain acceleration, A1. Now, a long time ago, people did a lot of experiments, and what they found out was that for a constant force, but a different mass, there's a relationship between acceleration and mass, as you would expect. If you apply the same force to a less massive object, say a tennis ball, it will have a certain acceleration. If you apply the same force to a much more massive object, say an automobile, it will have less acceleration. And what they found by repeating this experiment with different bodies and different masses was that the ratio of the masses of any two bodies equals the inverse ratio of the acceleration of those two bodies when each body is subjected to the same force. You can do this with as many different bodies as you want. As long as you apply the same force, this relationship will always hold. And you can see from this relationship that if my second mass is larger than my first mass, then my second acceleration is going to be smaller than my first acceleration. If my second mass was 5 times larger than my first mass, then the acceleration of my second mass is going to be 1/5 the acceleration of my first mass. Now we can multiply these two guys out here, and we find that m2 times a2 equals m1 times a1, and in fact equals the mass times the acceleration of any body subjected to the same force. And from here we get the equation force equals mass times acceleration. Now, we can redraw this or rewrite this as acceleration equals force divided by mass. And this brings us to Newton's second law of motion, which is that acceleration is proportional to force, and acceleration is inversely proportional to mass. And that just makes common sense. The higher your force, the more your acceleration. The lower your mass, the more your acceleration. So there's nothing mysterious about this. Okay, now the question is, how did I get my body from here to here? Well, I pulled on it, but what does that mean exactly? We know what it means intuitively, but what does it mean in the world of math and physics? Here's my body. I'm moving it from this point to this point. I grab it and I pull it over here. Now, when I let go, obviously it's going to fly back. The reason it's going to fly back is because there is a force acting on it. And we decided up here that we were going to call that force F. But if I'm pulling on it, if B is motionless over here, I'm pulling on it with another force, and that force has to be equal to this force. So the way we can write that is that the force pulling from, let's say, x2 to x1 equals the force pulling from x1 to x2. That's just common sense and common experience. But that brings us to Newton's third law, which is that for every action there's a equal and opposite reaction, and action implies acceleration, which implies force. Now, I said up here that the bodies were moving about with no friction, and that is hardly ever true in real life. You come close to it on an air hockey table, and in fact there are things called air bearings that are used in some machinery that have very, very low friction. But in real life you're going to always have some sort of friction. And there's two kinds of friction. There is static friction, which we'll call little f sub s. And there is kinetic friction, which we'll call little f sub k. Everybody knows what static and kinetic means. Static means static, it's not moving. Kinetic means it is moving. And just like there's 3 laws of motion, there are 3 laws of friction. The first law of friction is that the frictional force is proportional to the normal force. The second law is that frictional force is independent of the area of contact between the body and the surface that it's moving on. And the third law is that friction is independent of the velocity. And this third law was figured out by a French physicist named Charles Auguste de Coulomb in 1785. And Charles Auguste de Coulomb is someone we'll come back to very soon when we start talking about charge.